Hi everyone, welcome back to the channel. It's great to have you here again. In today's demo, we are diving into one of the most essential tools every DevOps engineer and system admin should know, SSH, that is Secure Shell. Whether you are connecting to remote servers, managing containers, or working with Ansible and Terraform, SSH plays a key role behind the scenes. So, in this demo, we will break down what SSH really is, how it works, and how you can start using it securely and effectively. Let's jump right in. Let's start with the basics. What exactly is SSH? SSH stands for Secure Shell. It's a network protocol that allows you to securely connect to another computer or server over an unsecured network, like the internet. Think of it as your secure tunnel into remote systems. You can log in, run commands, transfer files, and manage servers, all without exposing your credentials or data. SSH is widely used in DevOps, cloud administration, and automation tools like Ansible and Terraform. Basically, anywhere you need a secure remote connection. In short, SSH is your safe doorway to remote management, ensuring whatever you do on a remote system stays encrypted and protected. Now that we know SSH stands for Secure Shell and it helps us connect to remote systems securely, let's see how it fits in with other network protocols, like the ones we already use every day. When we browse the internet, we usually use HTTP or HTTPS. That's the protocol browsers use to communicate with web servers. Basically, how websites are loaded securely in your browser. But SSH serves a different purpose. Instead of loading websites, it's designed for secure remote command access. On the right side, you can see the flow. An SSH client, which could be your local machine or terminal, connects to an SSH server that's running on the remote system. This connection happens over port 22, which is the default port SSH uses. So, in simple terms, while HTTP or HTTPS is for web communication, SSH is for secure system administration and remote access. So, we just saw how SSH is different from protocols like HTTP and it's meant for secure remote access. But let's make that a bit more relatable with a simple example. Imagine this. You are at home and you want to control your friend's computer, maybe to fix something, check files, or run commands. Now, doing that over the internet could be risky if the connection is not secure. Someone could intercept what you are typing or see your password. This is exactly where SSH comes in. It lets you connect to another machine remotely, just like this example, but in a completely secure and encrypted way. So everything you type, every command, every file transfer goes through a protected channel that keeps your data safe from prying eyes. So in short, SSH is like having a private locked tunnel between your system and the remote computer. Now let's summarize what SSH actually stands for and what it really does. SSH literally means secure shell, and that name says it all. It's a secure communication protocol that allows you to connect to and control remote systems safely over the network. Every bit of data you send, your username, password or command output is encrypted, meaning no one else can read it even if they intercept the traffic. So, whenever you hear SSH, think of it as your encrypted shell access to a remote machine, which is secure, private and reliable. Let's see how that actually looks in action. Here's the simplest way to visualize how SSH works. On the left, you have your computer, which acts as the SSH client. That's where you type your commands, like connecting to a remote Linux server. On the right, you have the remote server, which is running the SSH service, waiting for incoming connections on port 22. And in the middle, this is the key part. We have an encrypted SSH connection. This means everything you send from your local machine, like commands, configurations or files, travels securely through this encrypted tunnel to the remote server. The server's responses also come back through the same protected channel. So, even if someone tries to intercept the traffic, all they will see is unreadable encrypted data. Your session remains fully secure. But how do we actually start that connection? Let's look at the basic SSH command. This is the most common SSH command format. SSH username at hostname. Let's break it down. The first part, SSH, tells your computer to start a secure shell session. Basically, to begin that encrypted connection. Next, username is the account name on the remote system, the user you want to log in as. And finally, hostname can be the IP address or the domain name of the remote server you are trying to reach. That's it. One simple command and your secure session begins. Let's check that really quick. Alright, so here on my AWS console, you can see the EC2 instance I have created earlier for today's demo, SSH demo instance. I used the Ubuntu AMI and this is the public IP address of my instance. Now I want to connect to this server using SSH from my local terminal. Let's try that. So here is the command I am running. SSH-i. So here my SSH key file is stored inside the .ssh/AWS keys path on my local machine. So I am providing that file with the -i option. The username is Ubuntu. Since this is an Ubuntu based instance, and after the @ symbol, I am passing the public IP from the AWS console. So once I hit enter, you can see it connects successfully. It shows welcome to Ubuntu. That means our SSH connection is now active and fully secure. Let's verify that by running a few simple commands. I'll type pwd, the present working directory, and you can see it shows /home/Ubuntu. That confirms we have successfully logged into the remote Ubuntu system. Let's try who am I. It shows Ubuntu user. Now I will type exit, and you can see connection closed. That means our SSH session has ended cleanly. We will explore more details about EC2 instances and other AWS features in upcoming sessions. But for now, our SSH connection is successful. By the way, whenever you are practicing with AWS, it's a good habit to stop or terminate your demo instances once you are done. That keeps your setup secure and avoids extra charges. Now that we have seen how to connect to an EC2 instance using SSH, let's quickly look at what's actually happening behind the scenes during that connection. Here's a simple breakdown of how SSH works internally. Step 1 is the connection request. When you type that SSH command from your local machine, the SSH client sends a connection request to the remote server. In our case, the EC2 instance running Ubuntu. And step 2, authentication. Once the server receives that request, it tries to authenticate you. This can happen either using a password or more securely with a private key, like the .pem key we used in our demo. And step 3, encrypted tunnel created. After successful authentication, SSH sets up an encrypted tunnel between your computer and the server. That means all the commands you type and all the responses you get are safely encrypted. No one in between can read or tamper with the data. So every time you connect to a server using SSH, you are not just logging in, you are establishing a secure encrypted channel for communication. This secure tunnel is exactly why SSH is so widely used in DevOps. Whether it's connecting to servers, running automation with Ansible, or managing cloud resources. Let's look at how we actually authenticate ourselves, and there are two main ways. The first method is the classic password login. You simply enter your username and password to access the remote system. While this works, it's not very secure. Passwords can be guessed, reused, or intercepted if not handled properly. That's why we mostly use the second method, key-based login. In key-based authentication, instead of typing a password, we use a key pair, one private key and one public key. The private key stays safely on your local machine, while the public key is stored on the remote server. During login, SSH uses these two keys to verify your identity without ever sending the private key over the network. This makes SSH key authentication much more secure and reliable than using passwords. Now that we have seen how SSH authentication works, let's understand what actually happens after you log in. Specifically, how users and permissions are handled in Linux. In Linux, everything you do happens under a user account. A user represents an individual account. For example, when we connected earlier, we logged in as the Ubuntu user. Each user has specific permissions, like which files they can access or modify. Now, multiple users can be part of a group. A group is simply a collection of users who share the same permissions or access level. For example, users in the admin group might be allowed to install software, while users in the developers group might only have access to the code directories. So, when you connect over SSH, it logs you in as a specific user, and that user automatically inherits the accesses and restrictions defined for their group. This is how Linux keeps your environment organized and secure, by managing permissions at both the user and group level. If you type who am I or groups after logging in, you can see which user you are logged in as and which groups that user belongs to. In our earlier example, we logged in as the Ubuntu user. Let's see how these SSH keys are actually created and used. When you use key-based authentication, the first step is to generate a key pair. That means one private key and one public key. We can do this using a simple command called ssh-keygen. This ssh-keygen creates two files, a private key which stays safely on your local system and a public key which you copy to the remote server. The private key should never be shared. It's like your personal signature or ID. The public key, on the other hand, can be freely placed on the server you want to connect to. When you try to connect, the server checks that your public key matches your private key. And if it does, it lets you in, all without any password. The best part is that this entire process happens securely and automatically, and the private key never leaves your local machine. You might notice different key algorithms like RSA or ED25519. These just refer to the type of cryptographic method used. ED25519 is newer and faster, and it's a great choice for most setups. Let's quickly connect all the pieces how SSH, ssh-keygen and sshd work together. Here's how the three main components of SSH fit together. It all starts with ssh-keygen, which is the command used to generate authentication keys, your private key and public key pair. Once you have those keys, you use the SSH command to connect securely to a remote system, just like we did earlier with our EC2 instance. On the other side, the remote server, there is a background process running called sshd, also known as SSH daemon. The SSH daemon listens for incoming connections on port 22, checks your credentials, verifies your key, and if everything matches, it grants access. So in simple terms, ssh-keygen creates your keys, SSH uses them to connect, and sshd handles the connection on the server side. You can think of it like this: you, the client, initiate the connection, and the building, the server, opens the door only if your key fits perfectly. And that's the complete flow of how SSH works, from generating keys to making a secure connection with the SSH daemon running on the remote system. Now let's understand exactly what it does. SSHD stands for SSH daemon. It's a background service that runs continuously on the remote machine, in our case on the EC2 instance. The SSH daemon's job is to listen for incoming SSH connection requests on port 22, which is the default SSH port. When your SSH client, that's the SSH command on your laptop, tries to connect, it talks to the SSH daemon on the server through a secure encrypted channel. The daemon then handles authentication, verifying your credentials or your key, and once everything checks out, it allows you into the system securely. In short, SSH is the client, SSHD is the server, and they communicate over port 22 using encryption. So every time you connect via SSH, it's your client talking to this SSHD process on the remote host. If you ever stop the SSHD service on a server, no one will be able to connect over SSH. That's how crucial this daemon is. Let's see how SSH authentication actually happens step by step. Here's what happens when you connect to a server using SSH keys. On the left, we have your computer, the SSH client. And on the right, the remote SSH server. When you start the SSH connection, the client and the server perform an encrypted handshake. During this handshake, the server checks if your public key, which it already has stored inside the SSH authorized keys file, matches your private key, which stays securely on your local system. If the keys match, the server confirms your identity and access is granted. Throughout this entire process, your private key never leaves your computer. Only the public key is shared and verified. This ensures a secure, passwordless authentication, which is why SSH key-based login is both safer and more convenient than using passwords. So, in short, your SSH client proves its identity using the private key. The server verifies it using the public key, and together they create an encrypted tunnel for all your communication. Let's quickly summarize everything we have learned. In a nutshell, SSH or secure shell is what enables secure remote access between systems. It ensures all the data transferred between your computer and the remote server is encrypted, keeping it safe from any unauthorized access. SSH supports both password-based and key-based logins. But as we saw earlier, key-based authentication is more secure and commonly used in real-world setups. And finally, SSH is an essential tool for managing Linux servers, which is why it's so widely used in DevOps, cloud, and infrastructure management. Alright, that wraps up our deep dive into SSH. In upcoming sessions, we will explore more AWS and Linux related topics. So, if you found this helpful, make sure to like the video, subscribe to the channel, and stay tuned for the next one. You can turn on captions. They are auto-generated but mostly accurate. Thanks for watching and see you in the next session.